All right, so for this problem, the object's 3 centimeters tall. It's 8 centimeters from a converging lens of plus 12 centimeter focal length. So now we're dealing with the situation where the object is very close to the lens. In fact, the object distance is less than the focal length. So I've already got it set up with 1 over the focal length minus 1 over the object distance. So that's 1 over 12 minus 1 over 8. 2/24. I don't know why that's plus there. That shouldn't be. Let's fix that. 2/24 minus 3/24. And so I'm going to end up with a negative value. So getting a negative value for the image distance in a lens problem tells me that the image is on the same side of the lens as the object. So I got negative 1 over 24. That equals 1 over the image distance. My image distance is negative 24 centimeters. Mr. Harding, let's use units here, please. And then the ratio ends up being, well, what am I going to have here? I'm going to have negative 24 over 8. That would be negative 3. But then this negative sign here turns the magnification into a positive 3. And that's where I'm derping it down here. I think that's where it should end up, that I have a positive image height, because there is no negative sign there. Ow. So I get positive 9 centimeters for the image height. And that makes no sense here. I think that image height looks like it should be 3. Oh, no, it's not. I'm sorry. I'm good with my math. Because this is my object right there. My object was 3 centimeters tall. My image is back here. Because the object is closer to the lens than a focal length, we get this magnified virtual image. And by my diagram, I got it 10 centimeters tall. By my math, I got it 9 centimeters tall. It's following the same rules. The easiest one is a ray that starts at the tip of the arrow, goes through the center of the lens undeviated. This is the ray parallel to the axis on the left that bends through the focal point on the right. And then kind of the challenging one is the ray directed as if it passed through the focal point on the left side. So I line up my ruler with the focal point, the arrow, and the lens. And this light would travel that path on the left and be bent parallel to the horizontal axis of symmetry when it emerges from the lens. Something that I've not emphasized enough when you're doing these lens problems, we know that the refraction is occurring on 2 surfaces, but when you're doing a ray diagram, we just throw a line right down through the middle, through the vertical axis of symmetry for the lens. So this is a representation of a convex lens where I have the pointy parts pointing away from the center. And these rays are diverging when they emerge, so if we trace them back to where they appear to have come from, that's why this is the image location for the tip. And that's part of what makes this image virtual. Okay, this is using that convex lens as a magnifying glass. You cannot project that onto the screen. The image is located the same side of the lens as the object, located behind the object, and it is magnified. It's greater in size. Greater in size by about a factor of 3. Because my image distance is about 3 times my object distance. Negative image distance on the same side of the lens as the object. Alright. So those are kind of the iterations with the convex lens. Convex lens, when the object distance is greater than the focal length, you will get a real image. It will be inverted. It will be on the opposite side of the lens. And as you saw with the lab, you can get that magnified, of the lens lab, I should say. Some of your values as you got the lens closer to the bulb definitely were magnifying the filament. This is a situation where the object is less than a focal length away from the lens. you get a virtual upright image. All right? And then the last thing in here, oh, and Gavin, I think I figured out how to get you into this thing. So, are you in it? The class notebook?
Yeah, I am.
Perfect. All right. So I didn't do all these iterations on here because, I mean, they're just going to differ based on the numbers, but the results are kind of the same. So 5 centimeter tall object, 15 centimeters from a diverging lens. You'll note with the diverging lens, the focal length is given as a negative, so negative 5 centimeter focal length. So if it just gives you the numerical value for the focal length, if it's negative, that's a concave lens. If it's positive, that's a convex lens. Find the image distance by calculation, and the image size by using the scale drawing. Really, come on, man. All right. So I've already manipulated this to solve for the image distance. 1 over image distance equals 1 over the focal length minus 1 over the object distance. 1 over negative 5 minus 1 over 15. So negative 3/15 minus 1/15, negative 4/15. That gives an image distance of negative 3.75. And again, the negative is telling us the image is on the same side of the lens as the object. And then if I do the ratio here of image distance to object distance, negative of negative 3.75 over 15, I'm going to therefore get an object height of 1.25. It's a positive. The math is telling me that the image should be upright. If it's upright, pretty good chance it's virtual. So then over here by scale diagram, I'm important to label so I don't confuse my image with my object. So there was my focal point, negative 5 centimeters. Here's my object 15 centimeters away from the lens. When I'm drawing the diverging lens, I've got the little triangles tip in because the geometry is the glass gets skinnier towards the middle. I made it 5 centimeters tall. The easy way to remember is the one that starts at the tip, goes through the center, it's going to emerge undeviated on the other side because the sides of the lens are parallel in the middle. My other 2 rays follow similar rules to convex, but they're just slightly different. Because now, with a ray that, I'm trying to think, okay, I need to start from the object, not the image. So, with a concave lens, a ray parallel on this side is going to bend up as if it came from that focal point. So that's how I know to direct that. And then a ray aimed at the focal point on the far side is going to be bent so it emerges parallel on that side. Trace those 3 rays back to a point where they appear to have converged. And yes, this one straight through the middle was actually passing by that point. So the 3 rays appear to have all met at that point. That's my image location. And I get that distance to be, you should say, negative 3.75. I get the height to be 1.25. So by math and by scale drawing, there's some agreement there. So you get some practice with this on the mastering assignment. And then the other thing I threw at you was this FRQ. And I'll put my solution for that on this page as well, just so you've got some additional examples. Ooh, College Board is tricking me because they put the object on the right side. Ooh. This is where every textbook example is like I know, what are they thinking? Oh, you like go that direction?
I don't think you can.
I don't know.
I can only travel.
It only goes. Oh man. Alright, OneNote doesn't want to work on my phone. So I'll put this on there eventually so you have it. Alright, had we already checked out the Mirage? Has this been out in this class? It was out for ELL. We're looking behind the ELL class. Look at it. I gotta get a bunch of this sample. The heck is up with that? So,
Sorry, right here. Does it look like I'm pointing at it?
so what you're seeing is a result of double reflection from curved mirrors. The light is actually converging in the plane of the opening of that hole. And so what you're seeing is a real image, and that's why it's tricking your brain. Because the light is acting as if it's leaving that point right there. Okay? The mirrors force the light to converge right here, so that it's diverging from there.
Yeah, your perception of light.
Isn't that weird?
Really screwed up.
Okay? So then I had to show you that so I can show you this. Make sure you don't have anything that's gonna fall out of your pockets. It's a little bit bigger. But okay, see the geometry of this thing? I haven't broken it in 20 years. Might have to. Oh yeah, you can see I can work on my hand with this. Right. So dig how you look from afar in the concave lens. Okay, it's like have you seen this type of reflection before somewhere?
That's still tricks.
Whoa, what up with that?
Ah!
Right? You look deep inside your pores.
Ah! The world's worst.
And then when you get old like me and whiskers start to grow on your ear cheeks, you put these sluts so that you possess the mother.
Ah!
So far away, you see an upside down image. Really close up, you see a magnified image. What's hard to perceive about the far away is that the far away is actually a real image. So if you stand over this, like get right over the center and try to point right down the center, you can touch your finger. You might have to go like one at a time.
Yeah. Oh, gosh. That's
Your hand comes out of the bowl, and that's like the most unnerving thing.
Okay.
It's like some Harry Potter business there.
They should make a human size one of those.
Real images are spooky AF, right?
Yeah.
Like a human size one of those,
Yeah,
would be like
you'd
coming
stand-
out of the portal like
You can
yourself.
stand out of it.
There we go. I think we got our project idea. We just need to get a really big, shiny little bowl. Don't actually touch it yet, Dolph. You don't touch it.
That's crazy. That's actually crazy.
Yeah. So that's concave. When you're beyond the object, or sorry, when you're beyond the focal length, you form a real image, and it's upside down, if you remember when you look at yourself from far away. But then really close up to it, you get a magnified image. Get that away before we burn out our retinas. Alright, so, concave mirror, convex mirror, where do you see these get used?
Oh, in hospitals.
Yep, right, to allow you to see around the corner.
Yeah.
Okay, and so if you look at yourself far away in the convex mirror, and then up closer. Okay, got it. And okay. So with this one, the image is upright or inverted? Upright. And then magnified or reduced. Yeah, even up close, got like a little pea brain there. So that's the convex mirror. It creates a wider angle of view. I should see more stuff. But yeah, it's got that going on. So let's put that over here. So that's our goal with today's activity and then over the weekend. And I have to remember it's Friday, so we're outie at 10:29. Huh? All right. So over here in the Canvas, there's a reading assignment. This is the last bit of chapter 34. You don't need to do that first. It's just on there as well. And then a pivot activity on curved mirrors. And the pivota. Let's see. This kind of works like the refraction lab that we did the other day. They've got a little bit of fogger and we don't have the sound. That's disappointing. So there's a series of 3 concave mirrors. And you can see with their apparatus over here, the rays that they're sending in are parallel. What do you notice about the reflected rays? Run that by your neighbor real quick.
There's a point. A bit to the right of his mouse that they seem to rotate now. Yeah, it rotates. It looks like it rotating.
Okay? So you're kind of seeing that. Like I strategically put my mouse somewhere specific. Now it doesn't hold at the extreme edges of the mirror, but for the most part in the middle, you can kind of see how all those parallel rays get forced through a point. And so part of that is using the tools to try to identify where that point is. And so I've got my ruler. I can set it here at 0. Now I'm zeroing. Come on, drop it. I'm trying to zero right here on the surface of the mirror. And I've kind of, this beam is going right off of the middle of the mirror, right? And so you can get a rough idea of where that spot might be that I knew to set my mouse, somewhere around here, yeah? So that's the focal point of the curved mirror. Parallel rays are forced through it-ish, right? Not perfectly. That's going to be the easy piece of data to collect. The more challenging piece of data is to try to get an idea of the radius of curvature for the mirror. To do that, I don't even know what that's supposed to be. The white box tool will give you some lines, and you can use those lines, and they can be rotated. And I want you to kind of work on your science sleuthing here a little bit, but you can get a bunch of these. And I want you to come up with a technique with these lines that's going to allow you to get an approximation for the radius of curvature. So it's those things that we're measuring. What kind of relationship is there between the radius of curvature and the focal length of the mirror? So there are 3 convex mirrors, three concave, and then there are 2 convex. And so if we play this one out, I think I heard Boaz use the word diverging. You can kind of see why and how that is. So with this, you're going to use those lines for a couple purposes. Okay, but there you can see how I can line it up with the reflected ray, kind of like when we did the mirror lab in class. And I can try to backtrace Whoa, what? Oh, of course. That's not helpful. But I can use these lines to try to backtrace and locate the point behind the reflective surface where the rays appear to have diverged from. Okay. And so that's kind of the latter part of the lab. So try to, with the first three, collect data on radius of curvature and focal point, find a relationship there, and see to what extent that seems to apply to the convex mirrors in trial 4 and 5. Okay? And so for this, you've got some spots to enter some of the trial numbers, okay, and the data you're collecting. And then the question I ask you at the end, based on what you observe in the videos, what appear to be the rules that guide ray diagrams for curve mirrors. Okay? So that's the activity. You've got about 20 minutes. If you want to work with your partner, each of you can do one of the concaves and one of the convexes, and then you're pretty much there. All right? Might be able to get it knocked out by the end of the period.